Welcome back to Let's Code. Today I was going to start doing some planet shaders, but I figured before I did that, maybe I should research what other people have done in the area so that I can get a nice head start on doing that. And that's when I came across the mesh that you see in front of you. So specifically, this is a mesh that is effectively a cube that is blown out into a sphere shape. So it's a unit cube that we've expanded into a sphere. So if we look at the wireframe and we look at the vertices here, we can see that as we scale up the number of squares or triangles on each side, we get a fairly uniform result from those triangles. Now, this is not true for other types of spheres. And before we get into that, I do want to say that I found this sphere from this Sebastian Leg video, which describes a bit more that I'll link in the description. So if you are interested in this topic, maybe in Unity or something like that, or just want to have another description of it, you can find that link in the description. So here we can see an example of the Cubesphere on the left, a UV sphere in the middle, and an icosphere on the right. Now, at first glance, it's easy to tell why the UV sphere isn't going to work for us. The triangles get super small and super dissimilar as we get towards the pole of the sphere. It's less obvious why the icosphere isn't going to work as well for us, because it seems like these triangles are even more uniform and really nicely distributed around the sphere. The issue for us is that the icosphere doesn't give us as much control over the number of vertices and the number of triangles that we have in the sphere. So in the Cubesphere, if you think about the cube as one face, we can scale up the number of triangles on one face, or the number of faces on one side of the cube, from 10 to 11 to 12 to 13 or whatever. And we get these very small increments, right? We add one set of triangles, one more set of triangles, one more set of triangles. Whereas in the icosphere, that's not true. If we upgrade the number of triangles that we need, we get far more and we get bigger steps. So you may be looking at this, and if you've noticed that I've bumped the icosphere and replaced the UV sphere in the middle here with a density of 20, you may be looking at this and going, yeah, but Chris, they aren't that different, right? Like, you don't really get that much out of doing a Cubesphere. Why create a custom mesh? And to that, I would say that I found the idea of a Cubesphere interesting, and that's why I did it in the first place. But second, if we want to do a level of detail for the sphere, depending on how close or far it is away from the frame, the Cubesphere will map almost directly to the sides of, say, a cube texture, for example, which means that the sort of planes on the Cubesphere also map to like a 2D array or a vec2 or a set of vec2s very directly, whereas the icosphere does not. So if we want to do level of detail with the planets that we're building, the Cubesphere turns out to be a better option because it fits into the programmatic nature of what we want to do a little bit better. So I'll leave this up on the side here as we go through this so that you can keep an idea of what we're actually talking about here in mind. So first of all, this builds on top of the game that we built yesterday, which is a two-dimensional gravity golf-based game. So we already have some code here, even though that code currently isn't relevant for what we're doing today. What we're doing today, because we already have a main.rs, I've set up some examples. And this is something that you get for free with Cargo. So you can put a file in examples, whatever. In this case, I have planets.rs. And then to run the actual example itself, you do cargo run -- example planets. And it'll look into examples. It'll use the same dependencies as the entire project. And your library and whatnot are available to be used in these examples. So what I've done is I've set up a very basic Bevy game inside of this planets.rs file that basically just sets up a clear color, a window size, the default plugins, the eGUI World Inspector plugin, and then this planet plugin that contains all of our logic. So now what we have is the main game in main.rs, but also a one-off kind of planet playground in examples planets.rs, which I find really interesting. You can kind of build these one-off tools using all of the same dependencies that you're building your core game out of, but you can fit them off to the side in sort of a special folder. So all of the logic for planets is in source planet.rs, and I've created a planet plugin, which is one way of organizing code in Bevy, that adds a material plugin for a planet material and then a wireframe plugin, which is why we can see the white outlines on each of these spheres. If we turned the wireframe plugin off, all of these white lines would just go away. And we've got a single system that runs called setup. The setup system does exactly 4 things. It spawns 3 cubes, so 1, 2, 3, at different places, and then it spawns the 3D camera so that we can actually see the cubes. Each of the cubes is built from a planet mesh, which we'll go over in a second, with a specific resolution. This resolution is the number of faces, or not the number of faces, but it controls the number of faces per side. So this is the number of vertices per face. So if we were going to go with 10, we would have 10 vertices on the x-axis, 10 vertices on the y-axis, and we would end up with a 9x9 grid of faces on that side of the cube. We also add a planet material to each of the meshes that we're spawning here. So the planet material shader, I haven't really done anything with yet. It's basically just a classic vertex shader, exactly the one that you would get from Bevy if you were just running this normally. And then the fragment shader just returns the vertex color in this case, because we do set the vertex colors on this mesh. So not anything super interesting in the shader itself, but we'll get into that later when we start putting more noise and more planet details into these spheres. So we've got 2 main concepts here. We've got the mesh that we need to construct, and we've got the material that we want to apply to that mesh. The material is responsible for setting up the shaders. So we've already gone over that on this channel. I'll go over it briefly here. But the mesh for this video is the more important thing. So constructing all of these faces and wiring them together. In this case, for the material, we implement the high-level material trait from Bevy, which is wonderful because we just pass in the WGSL file and we're basically done. We also have to derive as bind group, and we derive a type UUID, and that's it. That's the material. I love the high-level material APIs in Bevy. They're wonderful. So that brings us to the planet mesh, or the struct that we use to construct the mesh that we then actually send to the shaders so that we can render. We have a resolution, which I think I'm going to change the name of this to something like, I don't know, face vertices or something. Resolution is fine though. It's the same word that Sebastian used in their video. We can implement from planet mesh for mesh. So what this does means that back up top, when we do mesh from on our planet mesh struct, this will turn our struct into a mesh that we can then add to the mesh's asset database. So the from function requires that the from trait requires that we implement the from function. It also requires that this doesn't fail. So there's a different trait called try from. The try from trait could fail, but this from trait is meant to never fail. So in this case, we don't have any reason that we would fail, but just keep that in mind. The from function takes the planet mesh that we've passed in and then is responsible for constructing the actual vertices. In this case, we use vec3 y, neg y, x, neg x, z, and neg z to point in the direction of each face that we're going to build. If you're familiar with the concept of normals, you can think of this as the normal vector. So for y, we've got something like 0, 1, 0. For neg y, we've got 0, -1, 0, that kind of thing. We iterate over each of them and then call this face function, which is where the majority of our, really important logic lives. It constructs all of the vertices and a triangle list for each of the faces. This is important because the way that we need to actually construct this mesh is right here down below in this same function. So mesh new, we're going to create a primitive topology out of a triangle list. So a triangle list is something like 0, 10, 11, or something like that. Basically, it's one vec of a bunch of U32s that are indexes for building a triangle. So the first 3 numbers represent the vertices of one triangle. The second 3 numbers represent the second triangle, and so on and so forth. So every triangle requires 3 vertex indexes, and those indexes exactly match with the vertices vec that we pass in. So if we've got a triangle list and we do 0, 1, 2 as the indexes in that triangle, then the vertices that are going to be used to draw that triangle are the vertices at 0, 1, and 2 in this vertices vec. So it's basically a way of creating a vertex buffer over here and a list of triangles by storing the indexes of the vertices that we want to use for each triangle in one giant vec. So we set the indices, we set the vertices, we set the normals. So one thing about the normals here, that we don't actually calculate them specially. they are the same as the vertices in this case. So they're the same as the vertices because if you think of a unit sphere and you think of the points on the outside of that sphere, then if you have that point, what you have is a vec from the center of the sphere, which is at 0, 0, 0, to that point on the edge. So when we think about normals, we already have all of the normal values because this is a unit sphere, which means that all of the vertex positions are the vec that we would need for that normal. Again, when I say unit sphere, what I mean is that all of the geometry is somewhere in the range of -1 to 1. And then the way that we get the colors on this mesh is the same logic that I use in every other shader for debugging purposes. So we look on the mesh for the attribute position, which we just set so we know is there. If those vertex attribute values are a vec3 of f32s, which they are, then we get this positions. We can iterate over that and get each of the f32s for the x, y, and z coordinates, and we turn those into r, g, and b values. So in this case, the position attributes are something between -1 and 1. So if we do 1 minus -1, we get 2. 2 over 2 is 1. So that gives us our maximum value. If we do 1 minus 1, which would be the other direction, then we get 0. So we're getting colors from 0 to 1 here. So we put those all together, we collect them up into a bunch of RGBAs, and we set those as the attribute color. That color becomes this vertex colors attribute inside of our shader. So we can access it via color, which means that it's defined as out.color in our vertex shader, and it's just defined as color in our fragment shader. So now that we know what we're actually trying to build, we're trying to build up a giant list of all of the vertices for our sphere, as well as a giant list of all of the triangles for our sphere. In this case, if you look back at the running program here, you can see each of the triangles. So if we say start in the top left right here, we would go vertice, 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 and that would be like 0, 1, 2, 0, 2, 3, or something like that. And that would define this face right here. So our face generation takes the resolution that we want. So if we have, say, a resolution of 10, we get a 9 by 9 cube face. That is 9 faces by 9 faces, or 10 vertices by 10 vertices. We also pass in the direction, so we get the vec that we're actually using. So whether this is going to be the y-directional cube face or the x-directional cube face or something like that. And then we use this unzip function because face returns the list of vertices and the list of indexes for every individual face. So what we end up with is a tuple that's coming back from each individual face generation. And because this is a tuple, we can use the unzip function to take all of the values in each of the individual tuples for all of the results and turn them into a tuple of vecs instead. So this is going to be a vec of all of the first values for all of the face results, and this is going to be a vec of all of the second values of all of the face results. We take the list of vertices for the vertexes, and we have to turn them from a vec3, which is the value that we get back from face, into an array. We have to do this into an array because when we set the vertices later here inside insert attribute, for some reason that I am not aware of, the into trait or the from trait is not defined for a vec of vec3s, but it is defined for a vec of an array of 3, specifically to go into this function. So we just take the vec3 that we have with an x, y, and z, and we pack it into a single array where the first value is x, the second value is y, and the third value is z. And then we collect that. So we end up with a vec of an array of 3 f32s. And that's all of the individual vertices for every single face in order. We do basically the exact same thing for the triangle list. So the triangle lists is all of the triangles for each of the individual faces. We enumerate over that to determine which face we're actually dealing with at the moment. So the first face that we take here will probably be vec y because that's the way we defined it earlier. And this face ID is going to be a number from 0 to 5 because we have 6 faces. And then we get the list of triangles for that given face. We iterate over them, which gives us the individual index for every vertice in every triangle. So in this case, at this point, if we have one triangle in the vec, this number on the first iteration will be 0, on the second iteration will be 1, on the third iteration will be 2. So if we're dealing with the first vertice in the triangle, that could be a number from 0 to 99. If we are, again, using a resolution of 10, that gives us 10 vertices by 10 vertices, which is the total number of indices for any given face. So we have vertices numbered from 0 to 99. So local index is a number from 0 to 99. And then we add which face we're dealing with. So face 0, 1, 2, 3, 4, or 5. And we multiply that by the number of indices. So what we're doing here is we're taking each of the faces and offsetting them each by about 100. So the vertice numbers for face 1 are going to be IDs 0 through 99. For face 2 are going to be IDs 100 through 199. For face 3 are going to be 200 through 299, and so on. So we're just giving a new ID for each of these vertice IDs so that they match the index in the vertices array. So when our triangle refers to face number 1, or let's say this, when our triangle refers to face number 2, which is index number 1, so face ID number 1, and we want to refer to a triangle that is in, say, the bottom left, right? So maybe 0, 10, 11 would be a triangle starting at the bottom left that reaches up into the first row and goes 0, 10, 11. So up 1 and to the right 1. So if we start with local index 0, we get face ID 1 times the number of indices 100, which gives us the global ID for that particular vertex, or the index of that vertex is 100. So if we look at the vertices as we've combined them, we combine all of them into one long list of vertices. So for the second face, the 0th vertice on that face is going to be at position 100. And then we collect all of these into one giant list. So again, this is a triangle list. So the first 3 numbers are one triangle. The second 3 numbers are another triangle, etc. And that's it. That's the setup before we get into actually the face generation itself. So what we've done here overall is we've created each of the faces. We've packed all of those into one list of vertices and one triangle list of indices. And that's how we define any custom mesh. So that brings us to the face itself, right? So if we've got a cube face and we want to inflate that and kind of like blow a cube up into a sphere, we have to move them in some direction. So for face, we pass in the resolution, which in this case, we're passing in, say, 10, because it's an easy number to work with. And we pass in the local up axis. In this case, let's say the local up axis is the global up axis to make it easy for ourselves. So the axis here would be 0, 1, 0. 0 in the x direction, positive 1 in the y direction, and 0 in the z direction. We then create axis A as a swizzle of that original localized upward direction. In this case, we choose to do y, z, x, which for our purposes will create a 1, 0, 0 vector. That is 1 in the x direction and 0 in all other directions. What this gives us is the original localized, so 0, 1, 0, and then a rightward facing vector, which is 1, 0, 0. We take the cross product of those two vectors, which gives us the perpendicular vector, which in this case would be 0, 0, negative 1. So this vector setup is really important because we're going to be using these vectors to determine where these vertices should lay on the unit sphere. We'll go over them again when we need them. Then we create a new mutable vertices variable, which is a vec with some capacity. In this case, we know we're going to put in 99 vertices, so we can multiply the resolution, in this case 10 times 10, we know we're going to put in 100 vertices from 0 to 99. So resolution, which is 10, times resolution, which is 10, will give us the number 100, which gives us a vec with a capacity for 100 vertices. We do the same thing for triangles. So in this math, if we think about how many faces there are resolution minus 1 faces on each side of the cube. So if we do resolution minus 1, we get 9. So resolution minus 1 is 9. We get 9 faces on the x-axis, 9 faces on the y-axis for each cube face. Each cube face is made up of 2 triangles. Each triangle has 3 vertices, so we get 6 out of that calculation. We need to specify 6 indices to define one face. We have 9 by 9 faces, so we have 49 times 6, which is like 486, I think. So we have 486 indices that are required to define one face of this cube sphere. So for each direction, from 0 to resolution, which is 10 in the y direction, and 0 to resolution, which is 10 in the x direction, we let I equal both of the indices times the resolution. So if we're at 0.00, we get 0 plus 0 times resolution. If we're at 0, 1, we're actually at vertice 10 because we're at 0 on the x-axis and we are at y times resolution on the y-axis. So we're at the 10th index. If you go from left to right on x, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then it stands to reason that 10 would be the next level up on the y-axis in the first x position. So I is giving us the index, the local index for this particular face. So this will be a number from 0 to 99. Then we get this %x and %y. These are going to calculate how much of each of the axes that we calculated earlier are going to get added to the straight up vector, like the local up. In this case, if we have x over 9, then each of the x vertices is going to be 0/9, 1/9, 2/9, 3/9, and so on. Same for the y-axis. So we get a number from 0 to 9, or sorry, a number from 0 to 1 divided into ninths, and a number from 0 to 1 divided into ninths. So we take the local up, which in our case is global up, so 0, 1, 0. This is a vec3, remember? And we're going to add that to some percentage of the rightward vector and some percentage of the outward vector, or the z-axis vector, 0, 0, -1. So you can see that if we have, say, a %x, which is 4/9, that gives us something like 0.45. So we remove 0.5 from that, because what we're doing with that percentage is we have a number from 0 to 1 for how much influence this rightward vector should have. But what we want out of this is a number from -1 to 1. So if we subtract 0.5 from the location of the x-axis vertice, what we end up with is a vertice somewhere between -0.5 at 0 and 0.5 at 9. We can multiply that by 2 to get a -1 to 1 positioning for that vertice on the cube face. So by doing this, we've picked the x position along a -1 to 1 value. And we do the same thing for the y position. So if you think about our face, our cube face, as like this VS Code window or something, maybe we pick an x somewhere in the middle and a y somewhere in the middle, and then we're right here in the middle at 0. So what we've done is we've offset this x value to be somewhere from -1, 1 in the bottom left corner of our quad, 0, 0 in the middle of the quad, or 1, 1 in the top right. If we multiply this number by the axes that we care about, we can determine how far and in which direction we should move the upward facing axis to point at our new vertex position. So 0, 1, 0, remember, then we pick which x-axis we're dealing with, or which x vertice we're dealing with, and we multiply that by the rightward vector. So you can imagine if we get an x vector that is 0, then the rightward vector will have no influence. If we get a y vector that is 0, or a y vertice that is at 0, 0, then the outward, the z direction vector will have 0 influence. So what we'll end up with is just the local up, which means that the position for our vertex will be 0, 1, 0. And it's the same thing no matter what we do here. So we're just determining how far rightward or leftward and how far forward or backward each of these vertices needs to be. Now, these vertices aren't going to be perfect yet. They will be in the right position, but some of the numbers will be awkward to deal with. So what we do with that vector is we normalize it. And what that means is any vector in any position, right? So if we've got a vector that is like 5, 7, 23 or something like that, that vector is 5, 7, 23 from the origin, right? From 0, 0, 0. There is a similar vector pointing in the exact same position, the exact same angle, that is only length 1. And that's what normalize does. It takes that long vector that may be somewhere we don't want it to be, or a really short vector that may be shorter than 1, and it moves it to be length 1. Now, if we have, you can imagine, the right position for our vector, the right angle for our vector that we just calculated, and we know that the length of that vector is 1, then what we have is a radius of 1. So all of these points that we just calculated, by normalizing them to a length of 1 for that vector, are placed on this sphere. So all we need to do is push that vertice in, and it's somewhere on the sphere. The next step is fairly straightforward. We basically, as long as we aren't in the last row of vertices, we create 2 triangles. So in this case, it's I, which will be like, let's say we're at 0, 0, right? If we're at 0, 0, then I is 0. I is 0 plus 10 plus 1, so 11. 0 plus 10 is 10. So we draw a triangle from 0 to 11 to 10. And then we do the same thing, 0, 1, 11. So we go for the first triangle diagonally up to the right and then left. And then for the second triangle, we go straight to the right and then straight up. And that's how we define all of the vertices that will fit on a sphere from where we started, which was a cube. So we return all of the vertices and all of the triangles. And because we've done this in a way that represents any vector as up, we can point this vector in whatever face that we actually want to deal with, which there are 6 directions that we want to deal with. And then using this math, we can calculate where those positions for that particular face should be relative to a unit sphere. So that was it. It was very, very mathy today. That's because we were, dealing with vertice positions and meshes and things like that. I think that this is an explanation that very much benefits from visualizations. So I'm not saying I'm going to create it, but maybe there's a video to create here that is a little bit more visual and has a bit more of a straightforward explanation. But that overall is how we get this inflated sphere from a cube. So I'm pretty happy with that. It was not that much work to do today. Of course, I had to translate the original explanation from like Unity at World explanation to Rust and Bevy, but I think that worked out pretty well. And now we have this cube mesh that we can do anything we want with. So I'm going to continue with this and try to create little planets from, say, open simplex noise or something like that, similar to the way that like a Minecraft world would be created, where you have the Perlin noise defining how high or which biome a particular block is in. And then we'll create little worlds out of this and see what we can do. So that's it for today. I hope you enjoyed it. I hope the math was a little bit approachable for you. If it wasn't, don't worry. If it was something that you're interested in, but the explanation didn't quite land, let me know so that I know that there's people who want a more visual explanation, because I think we can make this explanation quite a bit better if I create, or if I spend a little bit more time and I create some more visuals for it. So we'll see. And I will catch you in the next video. Have a great day.